Do we, as a whole, live in a monstrous void? This seems like a logical inconsistency, considering the mind-boggling variety of the brilliant sky. It is, in fact, capable of addressing one of the greatest mysteries of present-day space research. The observed value of the Hubble constant just doesn't align with our theoretical models. The so-called Hubble tension could be explained by the reality that the Earth is situated in a sort of underdense bubble in space. However, although this notable methodology ultimately provides an answer to the discrepancy in the measured values, it also leads directly to another research quandary. According to our understanding, such voids in the universe simply should not exist. The subject of how fast the universe is actually expanding might seem straightforward at first, but in truth, it is one of the greatest mysteries of contemporary research. On the other hand, it has long been one of the fundamental facts of cosmology that the universe has been expanding continuously since its birth around 13.8 billion years ago. For a better understanding, it should be noted that the universe isn't expanding into a current space. No, rather, space itself is ceaselessly growing. As the universe expands, the individual galaxies also move away from one another. Furthermore, it should be noted that this occurs at a speed that is relative to the distance between the cosmic systems. This actually means that if universe A is twice as distant from Earth as galaxy B, its distance from us also increases twice as fast. However, to resolve how fast two galaxies are receding from each other exhaustively, we not only need to know their distance but also a factor by which we can multiply this distance. This is exactly where the Hubble constant becomes crucial, a parameter in Einstein's field equations that, contrary to its name, is not a constant at all since it is consistent in space but not in time. There are essentially two different ways to determine the corresponding value of the Hubble constant and thus the current pace of the universe's development. On one hand, there is the possibility of determining it with the help of the cosmic microwave background radiation that dates from the period not long after the Big Bang and fills the entire universe today. So, when scientists measure the cosmic background radiation and combine it with theoretical models of cosmic evolution, they arrive at a current expansion speed of 67 km per second per megaparsec. The critical issue, however, is that the actual measured values for the Hubble constant deviate drastically from the theoretical expectations and are fundamentally higher. In such a case, if the distance measurement depends on supernovae, redshifted galaxies, gravitational lenses, and variable stars, we are confronted with a Hubble constant that unexpectedly amounts to 73 km per second per megaparsec. Now, a difference of 6 km per second may not sound like much right away, but this changes dramatically when we consider that the expansion rate increases from 244,000 km per hour per megaparsec to 264,000 km per hour per megaparsec. On the other hand, this means nothing other than that the universe is expanding 20,000 km per hour faster today than it ought to be, according to the cosmological standard model. But how is that even conceivable? Have we misunderstood the universe? Well, the simplest explanation would be that the cosmic devil of error has sneaked in. According to this, a combination of measurement errors and inaccuracies in the past could have led us to currently have a research puzzle that isn't really a riddle at all. To actually check this, Adam Rees and his group utilized the James Webb Space Telescope to analyze over 320 supernovae in several galaxies, many of which had also been previously inspected by the Hubble Space Telescope. If anyone knows all about this subject, it's Adam Rees. After all, the American was awarded the Nobel Prize in Physics in 2011 for discovering the accelerated expansion of the universe through distant supernovae. In the case of the latest research survey, anyway, Rees had an alternate understanding: Webb should confirm the Hubble tension. Again, the new data also show a Hubble constant that is entirely higher than that obtained from the theoretically inferred models. Luckily, Rees also quickly knew an explanation for this astounding deviation. It may be the case that we have simply misunderstood the universe. Maybe we have overlooked something in our understanding of the universe, an unexplored force that has not been taken into account in the cosmological standard model. This could be another kind of particle or a misinterpretation of gravity. Moreover, it is possible that there is a strange form of dark matter or dark energy out there that is currently entirely unknown to us. Just a short reminder, neither dark matter nor dark energy has yet been directly identified. There are, therefore, only theoretical types of matter and energy that have been hypothesized to explain the motion of apparent matter on one side and the accelerated expansion of the universe on the other, where Einstein's theories waver. While Adam Rees directly alludes to the possible ignorance of the galactic research community, another group believes that they have finally addressed the enticing puzzle of the Hubble constant. The study presenting the novel solution was published in the journal Monthly Notices of the Royal Astronomical Society, and its essence can be summarized as follows: we live in a tremendous void in space. But what does this mean? After all, the brilliant sky, with its thousands and millions of objects, isn't what you would call void. Well, what is meant is certainly not a black night sky, but the assumption that our Earth is situated in a region of space where there is generally minimal matter. In comparison, this press is distributed by the Global Research Group for their study on the cosmic void, which is likened to an air bubble in a cake for illustrative purposes. Since the density of matter outside the scantily populated bubble is subsequently higher, the gravitational forces there pull the galaxies inside the bubble towards the edge of the void, and faster than would actually be expected. This would explain why the universe seems to grow quicker near us, or up to a distance of about 3 billion light-years, than in its entirety. The presence of areas with suboptimal density is, therefore, capable of eliminating this logical inconsistency in the standard model of cosmology. However, tragically, it simultaneously raises a completely different issue. In fact, the standard model doesn't accommodate such underdensities at all. They shouldn't exist by any means, since matter in the universe ought to be evenly distributed. But there is a way to get around this new inconsistency as well. Yet this requires saying farewell to. Einstein's hypothesis regarding the idea of gravity suggests that it is conceivable that gravitational forces may ultimately act uniquely, in contrast to what Einstein expected. In actuality, this hypothesis has been around for quite a while. For their study, the specialists depended on a modified theory of gravity that the Israeli physicist Mordechai Milgram had proposed as early as 1983. This purported altered Newtonian dynamics, or MON for short, explains the rotational behavior of galaxies by altering the conditions of motion of matter in the gravitational field. Accordingly, this speculation is also considered an alternative to dark matter. However, it is still the subject of heated debate and has not yet progressed past the status of a fringe theory. Nevertheless, this is the crucial point for the study's authors. Milgram precisely predicts the existence of underdense regions in space. If gravity truly acts according to Milgram's ideas, the issue of the Hubble tension would have vanished from one second to the next. Furthermore, one of the biggest mysteries in cosmology would finally be solved. Or is there no Hubble tension at all? Well, if Wendy Friedman has her way, then despite all new investigations and observations, we could ultimately be dealing with problems that don't actually exist. To understand what is meant by this, we need to return to Adam Rees's research. In this regard, the Canadian astronomer believes that dust, gas, and the effects of different stars can fundamentally distort the brightness measurements of Cepheid variables. This is because Cepheids are predominantly found in the disks of galaxies, where the stars are sometimes so close to one another that their light overlaps for a distant observer. To test their theory, Friedman and his group analyzed 10 nearby galaxies with the James Webb Telescope, which, in addition to Cepheids, also contain 2 other distance indicators. On one hand, there are red giants that are about to start burning helium in their cores. At this stage, the celestial bodies reach a natural brightness that is pretty much free of their composition and history. The examination of the apparent brightness thus allows conclusions to be drawn about their distance. The situation is quite similar for the other stars examined, which are further along in their development and enriched with carbon. Ultimately, the analysis, which required several years, concluded that the distances measured using the 2 new techniques are in very good agreement with one another and that they all yield greater distances than those determined based on Cepheids. Thus, it is possible that the Hubble tension is, in fact, due to the reality that we have adjusted the cosmic distance ladder incorrectly. Specifically, Cepheids are used to determine the lowest rungs of the distance ladder. If the lowest rung already contains a systematic error that subsequently runs through each subsequent rung, the value of the Hubble constant will definitely be distorted. However, we still don't know where exactly these errors lie and whether they truly exist at all. In fact, Adam Rees stresses that the Webb data he has gathered explicitly precludes the possibility that systematic measurement errors or distortions caused by the brightness of neighboring stars played a significant role. But now, you can assume the conclusive role of a new supporter. Please click on the approval and subscription button so you never miss another video from us in the future.